Hello dear students, welcome to Department of Chemistry, KTHM College, Nasik. So student, in our previous lecture, we studied the various factors affecting a thermogram. We studied the instrumental factor and even the sample factor. In an instrumental factor, heating rate was the important one. And the second thing is the furnace atmosphere. In case of a sample factor, the weight of the sample, then second particle size, then compactness of the sample. It was the important factor which affect over the thermogram in thermogravimetric analysis. Right now today we will discuss a few important limitations of a thermogravimetric analysis. Limitations of thermogravimetric analysis. Limitations. So the two important limitations are there. The first well-known limitation is about the physical state of the substances. Because we know that in a thermogravimetric analysis, we can analyze only solid sample. But we cannot analyze the liquid sample as well as gaseous sample. So you can say that TGA is applicable for solid samples only. It is applicable for solid samples only. Second limitation is related to the instrumentation. When we were discussing about the instrumentation, the central part of the TGA instrument is the sample holder. We call it as a cuvette, and this sample holder is attached with one important temperature sensor. We call it as a thermocouple. It means that the thermocouple is a device which measures the sample temperature. But one most important thing is that this temperature sensor, that is the thermocouple, is in contact with the sample holder, but it is not with the sample, and therefore the exact temperature cannot be recorded. Second limitation is that the thermocouple is in contact with sample holder, but it is not in contact with sample. Hence, exact temperature of a sample cannot be determined. So it was an account about the limitation. Now we will proceed towards some examples of a thermogram. We have to discuss a few demonstrative thermogram over here. If you wish to note this point, you can take a screenshot. Now the examples of a thermogram. First of all, we will discuss about the thermal decomposition of a copper sulfate pentahydrate. Our first example. Thermal decomposition of copper sulfate pentahydrate. When the copper sulfate pentahydrate is heated with a constant rate, the weight change with respect to temperature gives a corresponding thermogram, and the thermogram in a TGA is obtained in the form of a curve, just like a staircase curve. So we will get a corresponding curve in this way. It will be your weight, obviously it will be in milligram, and this is your temperature in a degree Celsius, and we will get a staircase like of graph over here. We have already studied about the nature of a thermogram. This is the horizontal part of the thermogram where the weight does not changes with respect to temperature. This is also a horizontal part where the weight does not changes with respect to temperature. This is also similar curve and this is also similar part of the TGA curve. It means that this is your CuSO4 5H2O. At about 100 degrees Celsius, copper sulfate pentahydrate start to decompose, and during this decomposition, some water molecule is evolved in the form of a water vapor. So the first reaction which takes place at 100 degrees Celsius is that the first reaction CuSO4 5H2O, when heated at 100 degrees Celsius, we will get the formation of copper sulfate trihydrate thrice H2O plus 2 moles of water will be evolved in the form of water vapor. It means that 18 by 2, 36 milligram weight will be the lost over here. So this is the loss in weight. It will drop down and we will get a corresponding copper sulfate trihydrate over here. Copper sulfate trihydrate, CuSO4 thrice H2O. Now this CuSO4 thrice H2O at about the 250 degrees Celsius temperature, 250 degrees Celsius, again further undergoes a dehydration, that is the loss of water molecule, and we will get a copper sulfate monohydrate. So the second reaction which start at about 250 degrees Celsius is second one, copper sulfate trihydrate at about 250 degrees Celsius, we will get copper sulfate monohydrate, again evolution of 2 water molecule in the form of water vapors. So again in the next case, further above the 250 degrees Celsius temperature to around the next temperature, we will call it as 300 degrees Celsius temperature, the next water molecule will be lost and we will get the formation of copper sulfate only. So this is nothing but the temperature at which the corresponding loss of water will take place. This is your around 300 degrees Celsius temperature. So the third reaction is copper sulfate monohydrate at about 300 degrees Celsius temperature. We will get anhydrous copper sulfate with evolution of 1 water molecule. Now again further when we heat the copper sulfate anhydrous at about 9073 to 11073 Kelvin temperature. The fourth reaction over here, when the copper sulfate is heated at about 9073 to 11073 Kelvin, we will get a corresponding copper oxide, sulfur dioxide and oxygen. So you will get CuO plus SO2 will be evolved as a gas. Along with that, oxygen will be liberated. So it was an account about the corresponding change. You will get CuO here. Again, if we heat this substance, this is corresponding temperature 9073 to 11073. If we heat it further around 1273 Kelvin, again the CuO combines and we will get the formation of cuprous oxide Cu2O. The reaction can be written over here. Fifth reaction, 2 moles of CuO at around 12,073 Kelvin, you will get the formation of Cu2O. Obviously, The byproduct will be the half of water molecule. So half of oxygen molecule, we will get a formation of corresponding product. So it was just an ideal thermogram. Now what we will get from this thermogram? The first important thing, in the first 4 reactions, means at about 100 degrees Celsius, 250 degrees Celsius and 300 degrees Celsius, there is loss of water molecules. So the water molecule will be evolved as a water vapor. So from these temperatures, we can get an idea about the drying temperature, or you can say the temperature required to remove the water of hydration, because these 5 water molecule which is associated with the copper sulfate over here, these are nothing but the water of hydration. So from this curve, we will get an idea about the water of hydration. Second thing, once we have to find out the ignition temperature for the copper sulfate pentahydrate, we will get a ignition temperature from this curve. So such a type of very important information we can collect from the thermogram. So it was our first example. In the same way, we can discuss about the second example also. Suppose if we took a second example of calcium oxalate, second example, thermal decomposition of calcium oxalate. Calcium oxalate monohydrate, I will call it as. When the calcium oxalate monohydrate is heated with a constant rate and the corresponding change in weight is recorded as a function of a temperature, we will get a corresponding thermogram. Again, the nature of thermogram will be the same. On one axis, we will write the change in weight, and on the another axis, we will write the change in temperature. The nature of a graph is again staircase like of graph, and we will get some horizontal portion, then vertical portion. In this way. This is your weight in milligram. This is the temperature in a degree Celsius, you can say. This is nothing but your CaC2O4H2O, calcium oxalate monohydrate. Obviously, initially there is no change in weight up to the 100 degrees Celsius. This is a common thing. The first water molecule, which is an water of hydration, will lost at 100 degrees Celsius temperature, and we will get the formation of a corresponding CaC2O4, calcium oxalate anhydrate, we call it as. This calcium oxalate anhydrate at the further temperature means 346 degrees Celsius temperature. 346 degrees Celsius temperature. Once the water will be lost at 100 degrees Celsius, temperature will rises. Now, further, if we go to the 346 Kelvin, this is the horizontal portion, no weight change will be there. And this is a 346 degrees Celsius temperature. It decomposes and to give a calcium carbonate, CaCO3, calcium carbonate. Again, this calcium carbonate at about 660 Kelvin, at about 660 degrees Celsius, we will get the formation of calcium oxide, CaO. And when the calcium oxide is again further heated at about 980 degrees Celsius temperature, it again further decomposes to form a corresponding oxides of the calcium. So we can write the reaction over here. just like a copper sulfate pentahydrate. Our first reaction will be the loss of water molecule. So CaC2O4 1H2O when heated at about 100 degrees Celsius, will you get a CaC2O4 plus H2O molecule will be evolved as a water vapor, loss of water molecule. In the second reaction, calcium oxalate, second reaction, CaC2O4 when heated at about 346 degrees Celsius, it will give the corresponding CaCO3, calcium carbonate, plus along with that carbon monoxide will be obtained as a product. So this is the carbon monoxide gas. Now again in the third step over here, when there is a formation of calcium carbonate, the calcium carbonate has a certain thermal stability. So with increase in temperature, there is a no decomposition. But when the temperature exceeds 660 degrees Celsius, it decomposes and gives the corresponding calcium oxide with loss of carbon dioxide. So the third reaction is that when CaCO3 is heated at about 660 degrees Celsius, we will get a calcium oxide plus carbon dioxide. And when this calcium oxide is further heated, they get decomposed. So this is an account about the various steps in a thermogram. I think these two examples are sufficient to understand what information we are getting from a thermogravimetric analysis and how we will apply it. So if you wish to note it, you can take a screenshot. Now we will discuss a few numericals based on thermogravimetric analysis. Very simple numericals will be asked in examination. So our first numerical is that 2 grams of calcium carbonate is heated at 200 degrees Celsius with 200 degrees Celsius with loss of CO2. Calculate the percent mass loss. Calculate the percent mass loss. So first of all, we will write the equation for this reaction, equation for this decomposition. Calcium carbonate CaCO3 upon heating at 200 degrees Celsius, obviously it decomposes to give a calcium oxide plus carbon dioxide. Here we have to find out the percent mass loss. First of all, we will find out the mass loss and then we will calculate the percent loss of mass. Okay, it means that we have to write the molecular formula of calcium carbonate. So calcium 40, carbon 12, and this is the 48 for oxygen. If we combine all these three, we will get a corresponding molecular formula 128 gram, 128 gram. So calcium oxide, 40 for the calcium and 16 for the oxygen. So this is your 56 gram. Now here 12 for carbon plus 32 for oxygen. We will get a corresponding 44 gram. From this equation, we got a one thing. If we decompose a 128 gram of calcium carbonate, there is a loss of a 44 gram of carbon dioxide. So our equation will be 128 gram of calcium carbonate loses 44 gram of CO2. So if you take a 2 gram of calcium carbonate, the corresponding carbon dioxide will be X, you can say. So we can go through the cross multiplication. That is 2 into 44 upon 128. X will be equal to. And if you do the calculation, we will get a value 0.6875. 0.6875 gram. So this is the amount of, or you can say the mass of carbon dioxide liberated when we heat a 2 gram of calcium carbonate. It means that 2 gram calcium carbonate loses 0.06875 gram of carbon dioxide. But if you take 100 gram, we have to calculate the percent. So we should consider 100 gram of calcium carbonate. So what will be the carbon dioxide? I will call it as Y. So we again calculate the Y according to our previous method, that is the cross multiplication. So 100 multiplied by 0.6875 upon 2, and here we will get a value of Y. Y is equal to 34.37%. 34.37%. So this is your loss of weight due to evolution of a carbon dioxide from the 2 gram of calcium carbonate, and this is the percent loss. I will call it as a percent mass loss. Got it? Okay. You can take a screenshot over here so that we will proceed to next example. Now the second example. 4 gram of calcium hydroxide calcium hydroxide is heated at 300 degrees Celsius temperature with a loss of a H2O molecule. With loss of H2O molecule. Calculate the percent of mass loss. Calculate percent of mass loss. So again, this is also similar numerical. First of all, we will write the equation for this decomposition. Calcium hydroxide, CaOH twice, when heated at 300 degrees Celsius, we will get the formation of a calcium oxide plus H2O in the form of water vapors. Mass number of calcium is 40 plus 2 times oxygen 16 plus 117, and it is a 74 gram overall. Similarly, calcium 40 plus oxygen 16, this is a 56 gram, and for H2O it is 18, means 18 gram. From this calculation, in fact this is nothing but the law of conservation of mass. We have already studied the law of conservation of mass in our undergraduate studies. The mass can neither be created nor be destroyed, and therefore the mass of the reactant is exactly equal to the mass of the product formed. It means there is only rearrangement of atoms. Breaking and breaking is a different one. Means we are just rearranging the atom and we are getting another molecules. Mass can never be created, never be lost. And from that we can write the equation over here. My intention is that the 74 gram of calcium hydroxide will release 18 gram of water. So here we have to calculate the percent of mass loss. Again, as like a previous example, we will calculate the loss of mass and then we'll convert it into the corresponding percentage. So our equation is that 74 gram of calcium hydroxide loses 18 gram of water. 18 gram of water. But instead of 74 gram, if we use a 4 gram of calcium hydroxide, therefore 4 gram of calcium hydroxide, it will lose x gram of H2O. So value of x will be equal to 4 into 18 upon 74. If we do this calculation, we will have a value 0.9729. 0.9729 gram. So this is a mass loss. I have to calculate the percent mass loss. So the 4 gram of calcium hydroxide loses 0.9729 gram of H2O. If we took 100 gram, because we have to calculate the percentage, CaOH twice will give a Y gram of water molecule. We will again do the cross multiplication over here. 100 into 0.9729 upon 4. And if we do the calculation, our final answer will be the 24.32%. So this is your percentage. Okay, you just note it by screenshot. Now the third example. TGA of a gypsum TGA of a gypsum. Gypsum means calcium sulfate. CaSO4 NH2O. The number of water molecule, that is the water of hydration, is not mentioned. N is written over here. Calcium sulfate NH2O. Shows mass loss of about 21% of original sample. Mass loss of about 21% of original sample. The temperature for complete dehydration is The temperature for complete dehydration is 170 degrees Celsius. Determine the number of water molecules. Determine the number of water molecules. Okay, two important things are given. First one, for the TGA analysis, gypsum is used. The mass loss is about 21%. That is the delta M. Is 21%. The temperature for the complete dehydration is 170 degrees Celsius. So the temperature is 170 degrees Celsius. Determine the number of water molecules. The chemical equation will be the very simple one. CaSO4 NH2O will give a CaSO4 plus n number of water molecule. As like our previous example, if you calculate the molar mass of the calcium sulfate, it is an 136 plus N times water molecule. For one water molecule, 18 mass is there. So 136 plus N 18 will be the overall mass of gypsum. This is again 136 gram. This is again 18 N, or N 18 we will call it. So from these values we can write the equation, and our equation will be in this way: 136 plus N 18 gram of gypsum will lose N 18 water molecules. And therefore, if we took 100 gram of gypsum, it will lose how many water molecules? So obviously, the percent loss is given. Out of 100, 21% loss is there. So if we took 100 gram of gypsum, the loss of water will be the 21 over here. Got it? So we can do the cross multiplication. We will have one important equation over here. So 100 into N 18 is equal to 136 plus N 18 multiplied by 21. So again, we can simplify the equation. 100 into 118, we will write directly over here. 1800 N 1800 is equal to 136 multiplied by 21, 2856, 2856 plus 18 into 21, 378, N into 378. We can shift the values on that side. 800 minus N 378 is equal to 2856. If we subtract these two values, we will have 1422 N. It is equal to 2856. Obviously, N is equal to 2856 upon 1422, and therefore N is equal to 2.0084. What is this N? N stands for number of water from the gypsum, and we have to calculate the same. Determine the number of water molecule. So your answer is that 2 water molecule was there. So our given gypsum was calcium sulfate dihydrate. So students, in this way, we finish our first session of this chapter, that is the thermogravimetric analysis. In our next lecture, we will discuss about the differential thermal analysis. Thank you.